Hello, everyone. My name is Oleg, and I'm a PhD candidate from the RMIT University in Melbourne, Australia. My co-authors are Guillermo and Nicola from the University of Padua, and my advisors, Shane and Falk from RMIT. In the paper, we review the current evaluation in QPP and propose an improved approach. But first, I'll go over the definition of QPP. Then I'll review the current evaluation, and after going over some related work, I'll present the limitations in the existing evaluation framework. After that, I'll present our proposed framework, and finally, I'll present some empirical results that will hopefully help to convince you in the merits and benefits of the new framework. So formally, the task of query performance prediction, QPP, is estimating the effectiveness of a search performed in response to a query without relevance judgments. It is common to divide the methods into two main categories, based on the prediction time with respect to retrieval. The pre-retrieval methods analyze the query expression using linguistic or statistical features, and the post-retrieval approaches additionally analyze the result list of the retrieval. QPP methods were developed over the last 2 decades. Now, to some potential applications that make QPP appealing. It's known that systems can exhibit high variance in performance over different queries. Even systems that are good on average may fail for some queries, and it's extremely important to be able to identify failures, as the poor search result that doesn't satisfy the user information need may lead to dissatisfaction of the user, since individual users care about their own search result, not the system's average. So the most straightforward application of query difficulty prediction is direct feedback to the user. With a reliable feedback, the user then can choose how to act, whether to reformulate the query and try again, or to use a different information source. This one is an example from Google. The system identified that the search result will unlikely satisfy the user and displayed a feedback message to set the expectations and provide some helpful tips. It can also be used for feedback to the system. That way, the system can select a better method of retrieval. Examples to this include selective query expansion, where the underlying assumption is that hard queries suffer from automatic query expansion, while good queries get a boost to performance. Federated search, where the system may select the best corpus to use for each query, or it can be used in Fusion to weight the initial results for a better final single result. It can also be used in conversational search, where the system decides whether to display the answer or take a different action, such as, for example, asking a clarifying question. As an example, a recent work studied the usage of QPP features in the QA task, under the restricted setup that a system can either provide one answer or not at all. Another application where the effectiveness of queries is estimated is query suggestions. This is a common example from a search engine, and here the user starts typing a query and the system provides several possible suggestions. And lastly, it can also be used for identifying missing content in the collection. It can be specifically useful for technical collections, such as a professional portal, to identify knowledge gaps. In order to have reliable QPP methods, we first need to be able to properly evaluate them. The task of QPP can be also divided by the goal. Mainly, we can split it into 3 separate goals, each with its own task and therefore suitable evaluation methods. So the first goal and task would be identifying search failures or hard queries. The general task here is classification. Therefore, suitable evaluation measures would consist of accuracy, area under the ROC curve, the F1 score, etc. Second one is predicting a retrieval effectiveness measure, such as AP or NDCG. The general task here is regression, and the suitable evaluation measures would be R-square, mean absolute error, root mean square error, and many more. And the third goal is ranking queries based on effectiveness or difficulty. The general task here is ranking, and suitable evaluation measures would consist of correlation coefficients, for example, or similarity or distance measure between lists of items, such as a candle's tau distance or experiment's foot rule distance, or many other measures that we commonly use in information retrieval. Now, going forward from here, I will focus mainly on the third ranking task, or more specifically on its evaluation. The existing evaluation framework for QPP relies primarily on correlations. Specifically, Pearson's R for linear correlation, which is a parametric statistical approach. And as a parametric approach, it's based on assumptions regarding the underlying distributions and their parameters. And two non-parametric approaches that are based on the order of the items instead of the actual values. Using these correlation methods allows a straightforward statistical significance testing. The hypothesis tested is whether or not there is an association between two variables in a population. Linear association with Pearson's correlation and monotonic with Spearman's and Kendall's. To simply describe the evaluation process for a single predictor, the correlation is calculated between the predicted values and the effectiveness scores of the queries. Here, on this plot, the blue dots are queries. On the y-axis, we see their AP scores, and on the x-axis, the scores assigned to them by the predictor, clarity in this example. The correlation is then calculated between the values, and in the example here, equals to 0.5. In fact, the most common method to measure effectiveness that was used in prior work on QPP is average precision. The usage of correlation to evaluate QPP was first reported in 1998. It was a Track 6 report where the NIST staff members were asked to classify each topic as easy, middling, or hard. After all the system runs were submitted, they have used Pearson's correlation to evaluate their predictions, and this correlation was reported. It was adopted as the main measure ever since. And it is simple and seems quite suitable for a single predictor. But what happens when we want to compare multiple different methods? So to compare multiple different methods, again, the correlation is used. The QPP method that achieves higher correlation is considered to have a better prediction ability. To test the significance of the difference statistically, the most common approach is to use resampling to create a distribution of values. Batches of topics are randomly sampled, and the correlation is calculated for each batch. Then, student t-test is usually used to determine if the difference of the means, the correlation coefficients, is significant or not. Now, for the research questions we address in this work. The first research question is, what limitations exist in the current evaluation practices of query performance prediction? How can detailed statistical analysis and testing be applied to QPP evaluation exercises? And what factors contribute to improving or reducing the performance of a QPP model? So, based on some of the related work, we find that generally, students' t-test is not the most appropriate for testing the difference among correlated correlation coefficients, as the independence assumption doesn't hold. Though there are statistical methods that were proposed to compare correlated correlation coefficients, such as Hotling's t-test or Fisher's Z-transformation, for example. The current correlation-based evaluation can't be generalized, and it is very specific for the system-predictor combination, not for the predictor. Moreover, it was shown that higher correlation doesn't necessarily attest for better prediction. And in the same work, the authors showed that when tested with proper statistical tests, many of the existing pre-retrieval predictors were not significantly different from the best predictor that had the highest correlation. And in some recent work, using query variants, the authors demonstrated that the relative prediction quality varies when queries with different effectiveness used to represent the topic. So to sum up the main limitations of the existing work, the correlation values are point estimates that are very hard to interpret unless they are really close to 0 or 1. Though using a single value for evaluation can be useful to summarize the efficacy, if we want to analyze the performance of a predictor, a single value is not enough. Since it is a single aggregated value over all the queries, we don't have any info for a specific query. So we can't, for example, identify if predictors fail on the same queries or not. The ability to analyze the effects of different system components is also very limited. For example, we can test how a stammer affects the prediction quality, but we can't significantly quantify the effect size or to compare it to the other components. It is not robust because we can compare only between predictions with exact same setups. And finally, it is not statistically sound either. Now, for the new proposed evaluation framework. Using a non-parametric measure, we make no assumptions about the distributions of the underlying data. Instead of aggregating the data into a single value, we create a distribution of values, which then in turn allows us to use well-grounded and sound statistical analysis. We define our per query error measure, the scaled absolute rank error. So the evaluation now is still an association measure between the list of queries ranked by their AP values and the list of queries ranked by the prediction scores. But now, instead of a single value aggregated over all queries, we have a distribution of per topic or per query errors. Now, if we still want a point estimate of the error, similarly to the mean absolute error, we define the scaled mean absolute rank error, which is simply the mean of the errors. This mean can be seen as a special case of Spearman's foot rule distance, making it a distance metric for the full rankings instead of a correlation. As for the statistical analysis, we apply ANOVA to determine if there are significant differences among the group means or not. For the ANOVA, we model the observations in the form of data equals model plus error, where the data is the explained or dependent variable, the model are the experimental factors. So, for example, if you would apply one-way ANOVA, model would represent the different predictors. And finally, the error is the variance in the data that is not explained by the model. In the paper, we use n-way ANOVA models. The first one consists of the different factors, such as the topic, the predictor, and other factors from the retrieval pipeline. And the second model consists of all factors and their interactions. Now, I won't go any deeper on the details of the different models here, but you can find the full details in the paper. After we observe in the ANOVA that there are significant differences between the groups, we apply a post hoc analysis. The analysis makes all pairwise comparisons and adjusts for the multiple comparisons. We've applied the Tukey's HSD test in our experiments, which is based on the studentized range distribution, studentized. The test defines confidence intervals for the differences between the groups. For the experiments, we used a well-known and reliable test collection, and all the data is also publicly available in order to support reproducibility. And specifically, the documents corpus we used was the Trek Robusto 4, with all its 249 judged topics and their corresponding title queries. Or as query variants, we used the Trek Core 2017 collection. The retrieval method was query likelihood, and the IR effectiveness measure was AP in order to be in line with previous work on QPP. In our experiments, we used multiple different QPP methods, both post-retrieval and pre-retrieval methods. In the table here, for example, the post-retrieval methods that we've used are Clarity, NQC, WIG, SMV, and all their UEF counterparts. Now, I won't elaborate on the different methods here, but you can find a short description in the paper. In total, we had 16 different QPP methods in our experiments. For the retrieval pipeline, we've used 3 different stemming configurations, 5 different stop list configurations, And this led in total to 15 different retrieval pipelines and a total of 240 different QPP retrieval system combinations. So first, we conduct a comparison of our proposed method with the existing evaluation method. To be aligned with the proposed method, we use a non-parametric correlation. In our experiments, we've used Kendall's tau as the representative of the correlation methods. It's simple and quite popular in the IR community. In this plot, we see a comparison between the new proposed point estimate to the existing correlation-based evaluation. We evaluate the predictors across all dimension pipelines, so we have 15 values for each predictor. Each box plot represents 15 values, and the line inside the box is the median and the dot is the mean. We can see here that the ordering of the predictors doesn't change between the two methods, and both methods yield similar results. Moreover, looking at the box plots, the distributions look quite similar. So when the proposed method used as point estimates, it is in line with the current evaluation. We also use the query variance to examine the evaluation when a topic can be represented by multiple queries. But first, we show the effect of the variance on the overall retrieval. On this plot, we have the PDF of the queries with their AP values. So for each AP value, on the x-axis, we see the frequency of it in the data on the y-axis. As we can see in this plot, the distributions are quite similar, and the scale divergence is 0.039, while the map values are 0.21 and 0.25. So adding the query variance doesn't skew the distributions. Now we explore the effect of the variance on the performance of QPP. Using the existing correlation-based evaluation, again, Kendall's tau, we create confidence intervals for the correlation coefficient, using Bootstrap for resampling and compare the predictor pairs based on the intervals to statistically test the differences. We see here that the intervals are much smaller when using the query variance, which is due to larger number of samples. But the order of the predictors wouldn't change much. As for the title queries, 57 pairs of predictors were found to be statistically significantly different out of 120 total pairs of QPP models. That's 47.5%. Now for ANOVA results. We ran ANOVA on the new proposed distribution of errors. And I'll present only the result for the first ANOVA model here. The second one, again, is in the paper. The topics were represented by the title queries, as it was done in previous work on QPP. From the ANOVA, we can see that for all the factors, there is at least one group that is significantly different. That is, the mean of that group is not equal to others. So all these factors have statistically significant effect on the prediction ability. Using the strength of association, which is a omega square column here, we can also quantify the effect size. Generally speaking, the larger omega square is, the greater the impact of the factor levels on the response variable. And here we can see that relatively to other factors, the topic has large effect on the prediction quality, while the effects of the stop list and the stemmer are really small. Following an ANOVA result, we use Tukey's HSD test to construct confidence intervals and test for pairwise differences. Here, the analysis is again for the first ANOVA model. Since the ANOVA is used to test the differences among the means, the confidence intervals are estimates of the new proposed SMER measure. Based on the HSD test, we found that 96 of the pairs are significantly different. That's 80% of the pairs, which is 64% more than what we found using the correlation method. So to sum it all up, we've defined the new per topic or per query error measure. The result of it gives a distribution of prediction errors instead of a single value, which then enables different statistical analysis. So one can still use, for example, a simple t-test, but it also enables more thorough options such as the ANOVA. It enables factor analysis to determine how different factors affect the prediction quality. and additionally enables a failure analysis for the QPP methods. So thank you for listening. I'll be in the ECIR session for questions, or you can send us an email with any further questions or comments.